This is part 11 in the Creed 7B restoration series. In the previous video I got as far as fitting the drive motor and refitting the speed governor, and I wasn't originally going to make this video, but I've had a few requests to explain how to adjust the speed on this. But I also thought I would go a bit beyond that because this is quite interesting, and in particular the way the speed governor works is actually quite interesting as well. When I first got this machine, I looked at the circuit diagram for this motor wiring, and this is the only diagram I've been able to find, and it shows this. So we have power coming in on the left, and it goes through a filter, it then goes through an inductor, and then through a switch, which is the run switch that turns the motor on and off, through a resistor, and then through the motor, and then back to the supply. In the middle we have this speed governor, and it's shown as being wired so that it shorts out the resistor. Now obviously in this mode, with this motor being wound as it is, closing the contacts on this speed governor would increase the current flowing through the motor, and being a series wound motor, the motor would increase in speed. This is a centrifugal switch, so when the motor speed increases, the switch would open and the current flowing through the motor would just be that supplied by the resistor, and the motor would start to slow down. The reason they have this parallel arrangement is you don't want all the current going to the motor flowing through the centrifugal switch, because otherwise the arcing would very quickly destroy the contacts. So about 90% of the required current flows through the resistor, and the governor is just there to make the small adjustments required to keep the motor at the correct speed. That not only reduces the current flowing through the governor contacts by a huge amount, but it also gives you finer control over the motor's speed. It won't hunt up and down quite as much. So looking at the way this is wired, I first try to test the motor without really looking at the circuit beyond that, and I'll show you what I found. This is the governor. You've got two slip rings, and these are the two brushes that connect, so that effectively they're here. So I'll turn the motor on. So the strange thing is, if I now release one of these brushes, you'd think that the motor would slow down or speed up or do something. But as you can see, when I pull the brushes away from the governor, it doesn't do anything at all. It just carries on at exactly the same speed. So obviously this is wrong. As it turns out, this is a shunt wound motor. I think I mentioned that in one of the previous videos, so this wasn't that surprising. It's not wired up as per the diagram. And the other thing that's odd about this, I'll turn this on again, and there's a, if you're familiar with how these should work, then you'll see that there's another issue as well with the motor startup. So I'll start the motor running. So you can see that not only does the speed controller not govern the speed, but also the motor is very slow to start up. So shunt wound motor, and it should start up fairly quickly if the governor is working the way it should. So I'll reposition the camera and show you what the problems were. If you remember, in the previous video I went to great pains to remove the governor cover, and that is why I did that, is I had to sort out whatever was going on in the governor because it just wasn't working. Okay, well hopefully this will come out on camera. In the governor there are two sets of contacts. We have this small contact here. You can see I put tape over the contacts. This is to simulate the problem I originally had. I've done quite a lot of work on this already, and the main issue I had initially was that the contacts were corroded and they weren't making contact. So to make this video, I've just put some tape over to demonstrate the effect. So the first thing we saw is the motor was slow to start up, and that's because this is the start contact. I'll explain this in more detail in a few minutes, but this opens pretty much as soon as the motor starts spinning, but it's there to provide very high start current to the motor. So if I now start the motor again, you can see it's very much quicker to start up. It's provided with a much higher start current, and then this will open to allow the governor to start to work. So both of these switches, there's this switch, there's another switch up here, this is a centrifugal switch, and they're both wired in parallel, so they both effectively short out the slip rings. So they join the slip rings together when they're closed. So this switch is normally closed, this switch is normally open. And again, because this set of contacts was corroded, I also put some tape over it to show you the effect it was having. But this switch, as I say, is normally open, and it closes when the speed builds up. So I'll start the motor again. You should be able to hear that it's going at a different speed. It's now going much slower. Also, if I pull one of the brushes away from the slip ring, you can hear that the governor is now having some effect. It sounds like the motor's running much too slowly, but it is at least now starting to work. So it's very strange when you first encounter this if you're expecting a Series 1 motor. And what I'll do before I go through the repair and the adjustment is just quickly explain how this governor works. If you're familiar with DC motors, then you can skip this bit. Otherwise you might find it of some interest. Okay, so what I have here is the budget version of the DaveCAD system. So what I'm going to do is just quickly explain how this governor works. It is quite interesting. So we have a motor which is shunt wound, so we have the armature fed through a pair of brushes. So there's a commutator here, and the current to the individual windings are supplied through the brushes and go into the windings on the rotor. So we have the power coming in here. And with a normal shunt wound motor, what you then have is the field coil would be here, and then this point will be connected to here, so these are in parallel. That gives you a nice high current in the field coil when the motor first starts up. It will accelerate rapidly and reach a stable speed. If you're not familiar with the concept of motors and the basic way they work, the thing to bear in mind is that the motor is always also a generator. So if you were to imagine you replace the field coils with permanent magnets, so if we replace those and we put a couple of magnets in instead to act as the field, then this wouldn't be here, of course. When you feed power to the motor, it's obviously going to spin up because we have a magnetic field that the rotor is sitting in. But if you were to plot the back EMF voltage, so in other words, the motor is acting as a generator all the time. Even when it's running as a motor, it's still generating electricity. The net result, of course, is it's absorbing energy, not creating it. But if you were to look at the back EMF being generated by the rotor at a given speed, it's always the same, irrespective of whether you're driving it or whether you're driving it with electricity or whether you're mechanically spinning it. So if you imagine you're mechanically spinning this, you'll generate a voltage that is proportional to the speed that it's turning at. So if this is voltage, this would be speed. And the faster you spin it, the higher the voltage you're generating. The difference is that the voltage you generate goes in the opposite direction to the voltage, or to the current I should say, that you're supplying when you drive it in its normal mode. And the way that the motor works when you apply power to it is it will accelerate fairly rapidly, generating higher and higher back EMF voltage, up to the point where this back EMF voltage is equal to the voltage that you're applying to the motor. And at that point it will reach equilibrium and it will stop speeding up. So in other words, it will follow this profile. If you increase the supply voltage, the motor will speed up. If you decrease the supply voltage, the motor will of course slow down. Now there's another way you can change the speed of the motor, and that is you can strengthen or weaken the magnetic field. So if you were to put stronger magnets in there, the motor would actually run slower, not faster. It would generate more torque, but because what you've effectively done is steepen this curve. So if you put a stronger magnet in, that's your supply voltage, that's the point at which the motor will stop accelerating. So if you have the same magnets we had here, then that's the speed at which it would reach equilibrium and stop accelerating. If you were to put stronger magnets in, then this same back EMF would be created at a lower speed, or reached at a lower speed, and the motor would do this. Okay, so in other words, it would reach equilibrium at a lower speed. Remember, this axis is speed. If you put a weaker magnet in, then the motor would generate less back EMF and it would reach equilibrium at a higher speed. So in other words, you can adjust the speed not just by changing the supply voltage, but also by changing the strength of these magnets. If we go back to the shunt wound motor, we don't use permanent magnets, we use a coil to generate the field. So that then implies that what we can do to regulate the speed of the motor is regulate the current flowing through this winding. And that's the way the regulator works on the Creed. There is a resistor in here. If you remember in the previous video, there's a huge resistor on the underside of the machine, and that's this. In this case it's a 50 ohm resistor. So if you were to run it just as it is here, it would switch on, accelerate fairly slowly and reach a fairly high speed. It would generate fairly low torque, but it would run at quite a high speed. And that's what we saw when the governor wasn't working, because this is effectively what the circuit was. It was just the resistor in series with the field winding, and that pair being in parallel with the armature. So the governor is actually wired across here. So firstly we have the start switch, and that is a normally closed switch, and it's opened as the speed of the motor increases. So when you first power up the motor, it's effectively wired exactly as a standard shunt wound motor is, and the 50 ohm resistor is bypassed, gives much higher starting current to the field winding, and you get a quite rapid acceleration. That causes the back EMF to very quickly start to build up, but then this switch opens and you effectively then switch from this line to this one, or this one depending on the value of the resistor. So just like in this mode, without anything else, it would accelerate fairly quickly up to, again, quite a high speed. We now want to be able to regulate the speed the motor is running at. So there is another set of contacts, but this time, so this is normally closed, but this time the contacts are normally open. And then what happens here is, by the time these come into effect, this is open, the motor is still accelerating, and then at some point this switch will close, it will short out the resistor. That will increase the current through the field winding, and then you'll jump from this curve back to this one. So in other words, it's trying to accelerate beyond a certain speed, but when the switch opens you jump back to this slope, and the motor will start to slow down. And that's the way that the motor governor works, is this switch will open and close, and it's effectively jumping you between the two speed curves. With a switch open, it's trying to run at the high speed. With a switch closed, it's trying to run at the slow speed. And the value of the resistor is selected so that these slopes are quite close together. And then it gives you kind of a nice controlled and stable speed. If these were a long way apart, you'd find that the motor would hunt and it would accelerate over quite a large speed range and then decelerate. And you don't want that, so they select a resistor that gives you this nice fine control over the speed. Another benefit of this arrangement is that as the load changes, then that also will tend to pull the back EMF down, because the motor will start to slow down, and that will tend to give you more time spent, if you like, on the steeper curve, and that will in turn mean that you're reaching your required speed even though there is more current flowing through the field winding. So in other words, it's automatically compensating for extra physical load on the motor. In addition to that, you have a further benefit that as the supply voltage changes, then again you will get a self-correcting mechanism whereby, because the back EMF it's trying to generate has to be higher to reach equilibrium, then that again will automatically correct for variances in supply voltage. So in other words, this arrangement, when properly organised, will compensate for basic speed, so no load speed. It will control the motor to a fairly fine tolerance. They specify it's plus or minus 0.5% in this machine, which is actually very good. It will also compensate for different loads on the motor, and it will also compensate for variances in supply voltage, and again they specify changes of up to 10%, and the motor will still run within its 0.5% tolerance. So it's very clever the way this works, and what I'm going to do now is just quickly show how to set this up. As I said, the problem I had was these two contacts were corroded and not closing at all, so it was effectively just a shunt wound motor with a 50 ohm resistor in series with the field winding. I do have one repair to make before I can start, which I'll just quickly show you, and then we'll get on to adjusting the speed of the motor to make sure it's correct. Okay, so looking back at the governor, another problem I had with this is even after I'd cleaned the contacts initially, the governor didn't work. It wouldn't govern the speed of the motor, and it turned out that this adjusting screw was wound all the way into this block, and the stop on the spring was hitting this stop lock before the contact was closing. And it turned out the reason for this is loose. There's supposed to be a clamping screw here that clamps this, but when I touched the screw I found out it was stripped. I'm not sure if it's even the right size screw, but there's no way that's going to clamp this block. So I'm going to just quickly change this and rebore it and tap it to an M3 size and fit a new screw. So I've actually made a special screw for this because I need to make sure that all the parts are the same weight, because obviously this spins at quite high speed and this is quite a long way from the centre of rotation, so I need to make sure that it's the same weight, including any material that I've removed. So I machined the head down to make it exactly the same weight, less the material I've removed from the block. Okay, so I'll quickly get this fitted and then get back on camera and we'll look at adjusting the speed. Okay, so this is the arrangement I'm going to use to adjust the governor speed. I've got the governor cover removed. In a previous video I said I was going to use a timer counter to adjust the speed using an optical pickup, but I realised that many people might not have that, so it wouldn't be that useful to demonstrate it that way. So what I'm doing instead is I have an ultra bright LED connected through to a signal generator. The signal generator is set to give a 1 millisecond pulse at 50 Hertz, and the frequency meter, the timer counter, is being used just to validate that the frequency is correct. You can see it's very close to 50 Hertz. It doesn't need to be this accurate, but this is just really to make it clear what the frequency is that I'm using. So the signal generator drives the LED. It's set to 50 ohm output, so it's got plenty of drive, and unfortunately you might not be able to see very clearly what's going on here because of the interaction of the camera shutter. What I'm going to do now is dim the lights. I'll put the camera back on a tripod and start the motor up, and then we should be able to see the strobe effect of the LED on this end cover of the motor. Okay, well hopefully you're going to be able to see this. As I say, it's going to be possibly a bit unclear because of the shutter speed of the camera, but I've got the LED pointing directly at this end drive sprocket on the motor, and we should be able to see the strobe effect as the motor's running. So I'll start up the motor and we'll see if we're anywhere close to the correct speed. Obviously what we're looking for is this to appear stationary due to the strobe effect of the LED. I've got the lights dimmed, hopefully not too far, hopefully you can still see what's going on. So I'll start up the motor. Okay, and it's going way too slow. So I'll adjust the adjusting screw on the governor, take it in quite a long way, and we'll see if we're any nearer. So I'll restart the motor. And we're closer, but still quite a long way out. So as I said, this governor is very precise, so it takes quite a few turns of the screw to make much of a difference in speed. So that was about 15 turns. We'll try it again. And hopefully you can see now that the apparent speed due to the strobe effects of the LED on the sprocket, the motor is much closer to the correct speed. Okay, so it needs to go a little bit further, still too slow. Try it again. And it's now getting very close. Turn the screw a bit further. Motor back on. A bit further still. So I'm going about 1.5 turns each time on the screw now, but we are getting quite close, so we should be almost there. Okay, so that's very close, probably only a turn or two away, so I'll give it another half a turn, try it again. Closer still, but still not quite there, another half a turn. Okay, that is now very close. As I said, I'm not quite sure how well this will come out on camera, but looking at it directly, it is very obvious when the speed is correct. You can see it very clearly, and the apparent speed of this, as I said, what we're looking for is to have it look almost stationary while the motor's spinning. And very close now. You can also see, incidentally, the variation in speed caused by the governor. And it is very close. It is surprising just how effective this governor is. We're getting very little hunting of the motor. It's very stable. Okay, give it another 1/10 of a turn. And try it again. Okay, again, I don't know if this is apparent on camera, but it does now appear almost completely stationary. I think I've gone very slightly too far, so I'm going to turn the screw back about a 1/20th of a turn. And try it again. Back very slightly further, and then that should be just about the right speed. Okay, so now the drive sprocket on the end appears to be, to all intents and purposes, stationary. We know that the LED is flashing at 50 Hz, and so we know that gives us a motor speed of 3000 RPM, which is what we're aiming for. I can now put the cover back on the governor. What I'm actually going to do is leave it spinning for a while to let the motor bed in, because I said I have cleaned up the commutator and undercut it, so I'll let it settle down. But as I said, this is now to a large degree self-compensating in terms of speed and supply voltage. So that's it for this video. If you want me to go over any more of this in more detail, then please drop a comment.